So hi everyone, welcome to Spacelink's talk that Dr. Robert Wicks is going to give us on planning missions. So Robert, if you want to maybe say a little bit about yourself and then we'll start the slideshow.
Absolutely. I'm a lecturer here at UCL, Mullard Space Science Laboratory. I used to work at NASA for a while and I've been involved in missions in lots of different ways. I'm a scientist, so I work on the data, but I've also helped assess whether missions should be launched as a part of a space agency panel. And I've also designed, launched, and operated my own missions. So I've done a bit of everything, and I'm going to try and cover all of those topics today.
Okay, that's brilliant. So I'm going to start the slideshow now, and let's share the screen. Okay, and here we go.
Can everyone hear me?
Oh, I'm sorry.
I guess everyone can hear us. We haven't heard lots of complaints, so that's good.
Let's do that. There we go. That's
excellent. Thank you very much. Yeah, so I was asked to talk about what it takes to go to space. So what do we do when we plan for a mission? How do we make a mission happen? And once it is ready to go, what happens when it's launched? So it's quite a broad topic. So I'm going to try and cover a little bit of everything. Go to the next slide. So it's, as I said, it's quite broad. There are lots and lots of different things you can do in space, and all missions are a bit different. But there are some common steps that most missions have to go through. The first thing you have to have is a really good idea for why you need to go into space. This is the why question. Going into space is very difficult and very expensive, so you have to have a really good reason. Once you have a really good reason, you need to develop a design for your mission. This is the how question. How are you going to do it? That means thinking about where do you want to go? How big, how heavy do you need to be? What instruments are you going to carry? Things like that. Once you have an idea of what you want to do and how you're going to do it, you have to win a process, a competitive selection process in a space agency. So our space agency in Europe is ESA. If you're in America, it's NASA. Does anyone know what JAXA and ISRO are?
Yes, is that the Japanese space agency?
Yes, JAXA is Japan. What about ISRO?
India?
Yeah, exactly right. So JAXA, ESA, and NASA are sort of the traditional space agencies, I think, from a European perspective. But more and more countries are getting involved in the space industry and in space science. And you can actually be funded to do a science mission from India, from China, Brazil. Lots of countries are expanding their science programs right now. So anyway, once you've had an idea, developed a design, got a space agency to agree to do it with you, you then have to build and test your equipment and your spacecraft. This is proving to the space agency that it'll work. Once you've proved that it'll work, you get to launch, which is a very scary and very exciting moment. But it's not the end. Once you're in space, you actually have to do the mission. So then you then spend some years receiving your data, doing your science, learning about the universe, and hopefully spreading the news to the wider world. So obviously I'm biased, I do this for my job, but I think it's amazing. And if you want to be part of a big team that works together on a very challenging but very rewarding thing, designing, engineering, building, testing, launching a rocket, using the spacecraft, being a scientist, and all these other things, then this is a great thing to do.
Oh, sorry, once again, if I could just ask if you could turn your mic off at your end, unless you're answering questions, just so the sound's a bit better. Thank you.
So let's go through those steps in a little bit of detail. Why do you want to go to space? As I said before, it's extremely expensive and very difficult, so you need an excellent reason. I've put 3 examples here of things that I know a bit about, or 4 in fact, because Solar Orbiter and Parker Solar Probe are 2 different missions. One, Solar Orbiter is a European Space Agency mission, and we're building some instruments for that here. Parker Solar Probe is a NASA mission, and both of them have this key question they want to answer: how does the sun work? You may have heard of Juno, which is a NASA mission, which is currently orbiting Jupiter. So the big question for Juno was, how do big planets like Jupiter form, and what is Jupiter made of? And you might have seen Rosetta in the news a few years ago. It was an ESA mission that went to a comet. So the big question for Rosetta was, what are comets made of, and how do they evolve as they get closer to the sun? So these are exciting science questions that could be used to motivate a whole mission. So my question to you is, can you name a mission that I haven't named? Have you heard of any other space missions, and what do you think its primary reason for existing is or was?
New Horizons, exploring what Pluto's like.
Excellent. Yes. Why would you want to know what Pluto's like?
Well, because it's a very distant celestial body, and we don't know much about it. So,
yeah, that's a great answer. Another sort of exciting question there is, where do planets come from? How do they form? And why are there lots of different kinds of planets? But that's a really great answer. Thank you. So if you had to design your own mission, or if you wanted to go to space, do you have a science question that you would like to study? Any volunteers? What do you think would make a good science question?
Well, we could do things about life. So personally, I would do one to go to Europa and explore the underwater oceans, the under ice oceans on the moon.
That is a really great answer. And the reason I think it's a great answer is that these questions have to be big. They have to be important. It's not enough just to be something no one's seen before. It has to matter. So does life exist somewhere else in the universe other than the Earth? Is a fantastic, important, exciting question that it is worth a space agency spending a lot of money on. So that's the kind of question we have to have as a reason to go into space. So the second thing after you have your question is you've got to design your mission to answer that question. So how are you going to answer your science question? And this is where you have to think about, where do you want to go? What do you want to measure? How are you going to measure it? And how are you going to get that data back? So the picture in the background there is the engineering design for Solar Orbiter. And we're going to go into that in a bit of detail in a minute. But these 4 questions here are really important, and it's worth digging into them in a little bit of detail because they drive everything about designing your mission. Space science missions are effectively autonomous robots that have to fly through one of the harshest environments that you can send a robot into, and they have to be 100% reliable. So it's extremely challenging, and you've got to answer these 4 questions really well to convince a space agency to fund you. So, for example, with Solar Orbiter, where is Solar Orbiter going? Well, we want to see the sun up close because its science question is, how does the sun work? So we should go close to the sun. This drives some important questions. You know, how much fuel do you need to maintain that orbit? And how can you survive in that orbit? So if you go close to the sun, it gets very hot. And you can see on the right-hand side of the design in the background, this big square kind of heat shield. So there are specific things in the Solar Orbiter spacecraft design to deal with where it is going. The second question is, what are we going to measure? So we want to know about what the sun is doing. So that means we want some photos of the sun, maybe in different wavelengths of light, to understand what's hot, what's cold, what's moving fast, where magnetic fields are. And we also want to know about the things that are coming off the sun. So that's particles called the solar wind and radiation. And when you're saying what you're going to measure, you also need to say, how accurately are you going to measure it? So this is the stage in thinking about your mission where you'd say, what do I need to measure? How accurately do I need to measure it? And how much do I really care about those measurements? So since we've said we want to take some photos and we want to also measure some in situ plasma, how are we going to measure it? Well, we need some telescopes and we need some instruments to measure the solar wind and the radiation. So we now have a list, maybe 3 or 4 telescopes to look at visible light, UV light, X-rays, and maybe 3 or 4 instruments to measure the in situ solar wind. So measure protons and electrons and radiation and magnetic fields. So you've designed a kind of conceptual, what we call a straw man payload of telescopes and plasma instruments. Then the fundamental question there is, next question is, how are you going to get that data back? It's all very well measuring it on the spacecraft, but it's no use unless we can transmit it back to the Earth. So we need to think carefully about how we're going to store the data on the spacecraft, how we're going to transmit it back, what kind of antenna are we going to use, and how much is that going to cost. For Solar Orbiter, there are two key problems. It's going quite far away from the Earth. It's going to orbit the Sun, and so it can be 2 astronomical units away from the Earth sometimes when it's on the opposite side of the Sun. And the other problem is sometimes it's on the opposite side of the Sun, and so the Sun gets in the way. So you can't always transmit your data back. So one of the key design constraints of Solar Orbiter was having a big enough hard drive essentially on board to store a whole orbit's worth of data, so it can be transmitted later when Solar Orbiter is closer to the Earth and the Sun isn't in the way. There is a competitor, or we don't like to think of it as a competitor, but NASA also has this mission Solar Probe Plus. So here is a little animation of Solar Probe Plus orbiting close to the Sun. It also has a big heat shield on the front. It is going much closer to the Sun than Solar Orbiter, and it has a very, or slightly different at least, payload. So I think there are some interesting things that we can learn from the fact that we have a NASA and an ESA mission both going to the Sun. So my first question to the audience is, do you know anything about Solar Orbiter and Parker Solar Probe? Have you heard about them before?
Yeah. Well, heard about them? I don't think we know a lot about them.
Okay. So both of them are going close to the Sun because they want to study basically why the Sun is hot and where the solar wind comes from. And you may kind of think, why do we need 2 missions to do this? And the first answer is a fairly silly political one, which is it's a really great science question that's important, and so both space agencies want to do it. And because they're separate agencies, there's no reason they can't both try. But then you come to the question of, if you're both trying to do it, why don't you have the same spacecraft design? If you've started from the same science question, how have you ended up with different spacecraft? And the answer is they focused on different ways to answer those science questions. Parker Solar Probe is the darker image on the bottom right there, and it's a bit smaller than Solar Orbiter. It has a bigger heat shield. It only has one camera, which is this coronal white light imager, which doesn't actually take photos of the Sun. It takes photos of the plasma that's coming off the Sun to the side. And then it has this in situ payload. So you can see there are some similarities. They both have this big long boom sticking out behind the spacecraft with magnetometers on it. And they both have in situ particle detectors. So that's low and high energy solar particle sensors on Solar Probe, and it's SWA PAS, which you might be able to see down the bottom on the Solar Orbiter next to the heat shield, and SWA HIS at the top there. So both of these spacecraft have those in situ payloads. What differentiates Solar Orbiter from Parker Solar Probe is all of the cameras. So you might be able to see in the middle these slightly brighter yellow things called STIX, EUI, METIS, and PHI, or PHI, as the Europeans like to call it. Those are cameras, and they are taking photos of the Sun through the heat shield. There's little holes in the heat shield to let the light through. Parker Solar Probe doesn't have any of those. So how are they different? Well, Solar Orbiter has lots of cameras, and Parker Solar Probe doesn't have any. Why are they different? Parker Solar Probe is going to go extremely close to the Sun. It's going to go within 9 solar radii of the Sun. So it's going to be the closest man-made object ever to the Sun. It's going to be the hottest spacecraft ever built, and it's going to be the fastest spacecraft ever built. It already is the fastest spacecraft ever built, actually. Solar Orbiter is going a bit further away. It's going to stay out near Mercury. But instead of going super close, it's going to take photos. So they have slightly different objectives. Solar Orbiter is trying to connect up the images it takes with the in situ data it takes. Parker Solar Probe is less worried about taking images of the Sun, but wants to go really, really close and sample the corona with its instruments in situ. So that's how we've ended up with 2 slightly different solar missions. And I hope it teaches you something about how the science objectives and science design of your mission can lead to different physical designs and different orbits for different missions, even though they're asking the same science question. So the next step, once you've got your science goals and the mission design, is asking someone to help you pay for it. So different countries have different ways of going about this. We're in Europe, so we use ESA, at least for the moment. So what you have to do in ESA is you wait for a call for a mission. So every 2 or 3 years, ESA will open a new call that says, we want to spend either an M class or an L class amount of money. So an M class is a medium-sized mission, which is £500 million. An L class is a large mission, which is more than £1 billion. So these, even medium is pretty large, if you see what I mean, but that's just the cost of launching things into space. These are both part of an ESA program called Cosmic Vision, which is an ongoing thing, a science program that ESA has with the objective of answering science questions for Europe. So one of these calls will open every few years, and it's typically more than 10 years before the launch. So you have to think up your science question and your mission design more than 10 years before it's actually going to happen. Answer one of these calls. So lots of people, everyone from around Europe that's interested in submitting a mission can do so. There are typically 20 to 30 mission proposals each time there's a call. Of those 20 or 30 proposals, 3 will be selected for a technical study. Those technical studies will last 2 years. And after the technical study, one winner will be picked. So you get 2 years of funding to do a technical study, convince ESA that your mission will work and that it's worth the money, and one of those will be picked. You then have 8 years to build and launch it. So let's assume that our mission has been through the preliminary phase of ESA selection. It's one of those 3 missions. What have we got 2 years to do? We have to put together a detailed justification for the primary mission goals. So we have to make our science question polished and come up with sub-questions for that science question. How are we going to answer them? Investigate additional secondary goals for the mission. Pick a payload of instruments which can answer those questions. You have to show very clearly how your payload will answer the questions that you have posed. You have to show that your designs are scientifically and operationally useful, and you have to show that you've thought through the pros and cons of your given design based on the resources you have. So a great example is the Mars rover, which you can see in the bottom left there. That's a NASA mission taking a selfie of itself on Mars. It is effectively a robotic car that drives around doing science experiments on Mars. So what they had to do was show that they needed to have a rover on Mars. They needed to have certain kinds of cameras, certain kinds of drills and scientific equipment. And then they had to give designs for those. So on the right there is a solar telescope, not on the Mars rover, but on a solar physics mission. So you have to show in your proposal at this stage a design for this telescope, how big it is, how much it will weigh, how it's going to work, and convince ESA that that's all viable. You then have to design your spacecraft and its subsystems. So you've got your science payload. You have to think about power, data handling, protecting the payload from any harsh environments like radiation, hot temperatures, low temperatures, things like that. And that leads to thermal stability. So on the right here, we've got an artist's impression of a mission called Ulysses, which was launched in the late 80s and ran for 20 years. And it's flying by Jupiter in this artist's impression. Where do you think this mission gets its power from? Any ideas?
The rocket that took it into space in the first place.
Yes, I mean, a rocket was definitely launched to use to give it speed to get to Jupiter. But now that it's at Jupiter, how do you think do you have any idea how it powers its electronics?
From the sun, so cell power.
Well, that's one viable answer, but this spacecraft doesn't actually have any solar panels. If you look at it, the sort of the drawing there, there's no big solar panels sticking out the sides. What it has instead is this black cylindrical thing that looks a bit like a Dalek's weapon from Doctor Who. That is a radioisotope thermal generator. It's actually nuclear waste in a way that is decaying, generating heat, and that heat is being turned into electricity. So this is just an example of different ways of powering your spacecraft. If you're going around the Earth or close to the sun, solar panels are great. But if you're going out beyond Jupiter, there's just not enough sunlight. It's too dark and too cold to use solar panels, and so you have to use other ways to generate electricity. And in this case, it's radiation. So your spacecraft and subsystem design has to support all of the operations of your science payload, and you have to prove that it's going to be reliable. This is a huge task, and one of the main parts of the proposal process. The other thing you have to do is think about your orbit. Where are you going to go? How are you going to get there? This is where the rockets come in. And when are you going to operate? When will your spacecraft turn on? Will it have different modes of operation? How much data do you need to transmit back to the Earth? And therefore, how big does your radio dish have to be? So this is a wonderful photo of an ESA antenna. It's 35 meters across. So it's hard to judge its scale from this photo, but that is absolutely huge. 35 meters is a good chunk of a football pitch, basically, and it can rotate to point in any direction. So you have to budget for your data, how much you can transmit back to the Earth, how many of these dishes are you going to use, and how much is that going to cost? And if you get picked, you then have to prove that this is a good idea through trade-offs. So you have to show that the amount of money you're going to cost is worthwhile relative to the delivery of your science goals, and that your performance of your spacecraft is good by trading off mass, power, and telemetry and things like that. You might even have to trade off different subsystems or instruments. It's quite common to have to drop an instrument from a mission. If it was only providing secondary objectives, for example, it will be one of the first things to be cut if you need to save some mass or save some power or save some money. Overall, you have to convince ESA that this is something that's extremely interesting, you're doing it in the best way possible, and that you can stay within the budget and time schedule. And unfortunately, that means a lot of paperwork. I'm not a fan of paperwork, but you shouldn't be put off by this. It's if you want to make things, complicated things like robots and spacecraft, that work, you need to have documentation. That is how you track whether things are going to work or not. The final step, once you've been selected, is building and testing. So on this slide are two examples of very different approaches to satellite design. So on the right-hand side, we've got Solar Orbiter again, which is being built by Airbus. So if you're going for a big mission, you might typically have a big company like Airbus or OHB or Lockheed Martin build the spacecraft for you, and then the scientific community would just provide the instruments. But there is a new wave in space science. Some people call it Space 3.0, and that is for much smaller spacecraft. So a great example in the UK is Surrey Satellites, which is a company in Guildford that can build small spacecraft for you. And the other is CubeSats. So the picture on the left is a CubeSat that we built here at UCL. And they are really, really small. So if I put this to scale against Solar Orbiter, it's something like that. The reason this is a good idea is that because they're smaller, they are a lot cheaper and they're a lot simpler. So you can build them much faster. The building of the satellite goes in parallel with the building of the science instruments, and that means you have to have really big teams with lots of different expertise to make this work. Engineers and scientists for sure, but also managers, support staff, the money people, all need to work together. So what does testing look like? Well, here is that CubeSat, UCL sat being built. You get the parts out of a box and you have to test them. You build a proto-flight model, so a test model, and test it thoroughly. So that's what the oscilloscope in the top right and pictures in the middle are about. You keep testing and testing and testing. I cannot say testing enough. It took us 6 months to test all of the different bits of this tiny satellite. But once you've tested everything you can possibly think of and everything works, you then build your flight model. You have to test that flight model by putting it inside a vacuum chamber and heating it up and cooling it down. And that proves that it'll survive in the vacuum of space and hot and cold temperatures. The picture in the middle with the excitable looking young man is our vibration test facility. So you put your satellite on a plate and you shake it very violently to prove that it will not fall apart when it's being launched. Then you finally weigh your satellite, so you know how much how much mass it has, to prove to the launcher that you can fit, and then you deliver it to the launcher. So the top right picture is UCLSat just before it went inside the housing it was going to go in for launch. And so yeah, the final, not quite final, second to final step is the launch, which is very dangerous but very exciting. So on the right-hand side, we have a launch from just a couple of weeks ago, Bepi Colombo, which is going to Mercury. And the picture on the left is UCLSat being launched from the space station. You can just about see UCLSat in the middle there, flying off into space. So yeah, that's very exciting. But it only lasts for a few minutes. Then you have to operate your mission. So this is the NASA Mission Control Center. And there are lots and lots of different roles once a spacecraft is working. If you've been working on the design and development of the mission, you've been doing that for more than 10 years. You may feel like the launch is the end, the success, but actually you have only just started, because you then have to operate your mission, typically for 5 to 10 years. All that data that you've been collecting has to be returned to the Earth. You have to calibrate it, release it to the public, so that scientists all around the world can use it to answer the science goals that you proposed. You hopefully might go on TV or radio to report your results to the world. You need TV presenters, video experts, and computer graphics experts to demonstrate what has been done, because you can't see your spacecraft once it's in space, and to provide useful learning material to explain the science results that you have. You need computer programmers to program and fix the spacecraft, because it will keep breaking, and the ground systems that support that spacecraft. And you need managers and support staff to run the operations. Project management and missions management is a real thing that you need experts in. Scientists and engineers like me are no good at it, or on average are no good at it. Some are good. But we need professional managers to help us with all that, with these technical things. So that is my mission life cycle. There is me working on UCLSat, and the bottom right picture is the team of people that worked on UCLSat. So we needed, not everyone is in that photo actually, we needed around 20 people to make this tiny satellite. So you can imagine when you have a big mission like Solar Orbiter, how many thousands of people have to work on it to make it possible. So who has questions?
Fantastic. I'm just going to end the slideshow so that we can go back and see the people we're talking to. There you will see my awful desktop, and I will stop the screen share. Where is screen share?
At the top. Green.
Stop. Oh, there we go. Fantastic. Let's put our camera back on so you can see us. Brilliant. Okay, our camera's there. So yeah, thank you very much for listening. Has anybody got any questions they'd like to ask? We'll start with team 1, I think.
Okay, yeah, I've got one. What effect does the launch vehicle that is being used have on the overall mission plan and how the spacecraft is designed?
That is a great question. It happens in a kind of iterative circle. So when you propose your mission, you're normally thinking, where am I going to go? So for example, I'm going to Jupiter. Well, I need a really big rocket because I've got to get lots of energy to get there. If you have a really big rocket, you normally have a very big fairing. That's the container on top. And so there's not much, well, there's always a constraint on the size of your spacecraft, but because you have a big fairing, you can normally build quite a big spacecraft. But when you're designing your mission, you might say, well, I want a really big telescope, so I need a really big spacecraft. And then you would go to the space agency and say, well, even though I'm not going to Jupiter, I'm only going to Earth orbit, I still want a really big rocket because I want to launch this really big thing. And so you will have a discussion backwards and forwards with the space agency to say, how big of a rocket can we afford for our budget in terms of money? And therefore, how big of a spacecraft can we have? So the rocket normally limits the size of your spacecraft, but the needs of your mission will hopefully push back on the design of the rocket, so you can have as big a one as possible. Well, that's a scientist perspective. I always want a big rocket because I want to launch the biggest possible spacecraft so that I can do the most science. ESA has a different perspective. They would say, we only have 500 million. Rockets cost 150 million plus. So if you want an expensive rocket, you better justify it.
Oh, that's brilliant. Thank you. Team 2, do you have any questions?
Yes. So
I'm really sorry, you're breaking up quite badly there. We couldn't hear you. Can you try asking again?
social issues. So we're looking at tackling like physical and social issues when you send people to space. So what would you say are the most?
Team 2, we can't hear very well. Can you use the chat box? You should have a chat box there, and you can write your question in, and then we'll be able to hear you properly.
You can try turning your video off as well if you want. That might get you some bandwidth.
Yeah. Again, this is a bit like, I guess, missions when you can't get all the data down that you want.
Absolutely, yeah. You have to prioritize your data.
So we'll just give them a moment for their chat box to come up and see what their question is. I had a quick question, actually. I was going to ask you, is it quite common then that you have sort of arguments between engineers and scientists about what's possible and what's the dream?
I wouldn't like to say arguments. I would like to say, organized, rational discussions. But yes, I mean, throughout the whole 10-year process, there will be trade-offs being made between, oh, I want to measure this thing as a scientist, and the instrument designer saying, well, I can't do that because it's too small, or it's too much energy, or it's too heavy, something like that. And so there's a continual process of improving designs by scientists and engineers talking together. I think that's one of the great strengths we have here in the UK, in that we have science expertise and engineering expertise that can work together.
Yeah. I've seen the questions come up. So the question is, what would you say are the biggest physical and social issues for astronauts living in space? We're looking at tackling these issues in their team.
That is a great question. I am not a huge expert on astronauts, but I think there's a few different things. It's extremely difficult to get to space. So launch is quite traumatic and stressful in terms of physical toughness for the astronauts. And then obviously being in a free fall environment once you're in space is quite bad for the human body. So you tend to lose muscle mass and bone mass while you're in space. So astronauts have to have a very thorough physical training program. In terms of social issues, I mean, you're a small number of people trapped in a very small space for quite a long time with no way to leave. So you have to have a good working relationship with your co-astronauts, and ideally there needs to be some set of procedures in place just to formalize things like your schedule and who's in charge. You don't want to be having arguments about who's right and who's wrong when you have to fix something. You need a clear command structure so that there are not ambiguities between personal responsibilities. Yes. ESA has a manned space program, which goes to the International Space Station at the moment, but manned space flight has just been kind of bubbling along in the way it has been for the last 20 years, I think. I'm hoping that in the next 10 years or so, we'll get a sea change. These new launch providers are, especially in America, are allowing NASA to spend money on new manned spaceflight vehicles. So NASA are looking at sending people to the moon and Mars, and that will be a real accelerator for manned spaceflight again.
Fantastic. If we go back to Team 1, if you have a question, and also in the meantime, Team 2, feel free to put questions in the chat box, and we'll get back to them as we go along. So Team 1, do you have a question?
Yes. So about human spaceflight, what kind of extra things we have to consider, and like how easy the spacecraft is to repair and things like that with human spaceflight?
Great question. The standards that we apply for robotic spaceflight are pretty tough, but any manned spaceflight, the standards are even tougher. So the what that means is the testing I was talking about becomes 6 testings instead of 3. So any bit of hardware, like a bit of the International Space Station or the transport vehicles that take astronauts there, are extremely hard to engineer and expensive. So the systems are very, very robust, but that often means they can be quite complex. So I think one of the big challenges for manned spaceflight is the expertise of the astronauts. Can they understand how all of these different systems work? Because, as you said, they have to be able to fix them if anything should go wrong. And there are obviously some systems that, if they fail, there is no chance to fix them. That's, the mission is over, if you see what I mean. Then those are the systems for which there are fail-safes and backup systems, and the designing and engineering of manned spaceflight vehicles is extremely difficult and interesting. Actually, it's you have to think of very imaginative ways of making sure that things can't fail. The classic one is the fail-safe, right? So in other words, fail-safe is a phrase that I think we use a lot in just normal human English language, but it actually has a meaning in engineering. When something fails, it should default to a safe mode. So an example is traffic lights. If there's a problem with a traffic light, they should go red. They don't go green when there's a problem. That's to make sure there are no crashes. And you need to do the same thing for as many systems as you possibly can for manned spaceflight, so that if they fail, no one dies.
We've had another question here from Team 2. So another one about human health. What solutions are already in place to help issues like loss of body mass and bone mass? Do you think they can be improved?
Great questions. Again, I'm not a huge expert, but I mean, there's well-designed exercise programs for the astronauts while they're in space. I think there are dietary programs and supplements they have to take. There's a lot of training before you get launched into space to make sure that you're in good physical condition. And then once you come back, there's also a program of recovery. I'm absolutely certain they can be improved, but it's a very difficult thing. Any medical process that is happens on humans is difficult to do, just from ethical reasons. And it's even harder with things in space. You can't simulate a zero-G environment on the ground. So there's no way really to test what happens to people exposed to zero-G for extremely long periods of time, other than the astronauts themselves. So in a lot of the experiments that happen on the International Space Station are the astronauts testing themselves about human biology. So the answer to your questions, hopefully, are coming from the International Space Station right now.
Also, one of the things they have to do, because obviously they can't use normal weights as you would in the gym, so they have to use resistance machines like bands and wires and stuff that provide tension and resistance so that you can keep your muscles going. I know that I saw a talk about some earthworms that were on the International Space Station, and they were monitoring their muscle mass loss, and they had things that the earthworms would move through that were different tensile strengths and things, so they could push things and pull things, and they would monitor how well the worms did after time in space. But I think something we also don't know at the moment, I mean, what's the longest somebody's been on the International Space Station is a few months, I think.
It's a few hundred days. It's slightly more than a year. I think it's like 400 and something days. Maybe one of you know.
Yeah.
But
for going to Mars, for example, or in the future even further than that, we're talking years, and nobody knows the effects of zero-G for years on humans.
That's true. And the other thing about missions to Mars, especially, is that the radiation exposure is very difficult to deal with. The International Space Station is only 400 kilometers up, so it's actually protected by the Earth and its magnetic field from a lot of the radiation. But as soon as you leave that magnetic field and go off towards Mars, your radiation exposure goes up. So it's a real, one of the biggest challenges about Mars missions is how to handle that radiation exposure.
So if we go back to Team 1 again and get another question from Team 1, if you have one.
Yeah, as a follow-up to our last question, from the perspective of someone who's designing things to be used in missions in space, are there any advantages to having the availability of human people to operate design?
Yes and no. So the problem with robotic missions is that if they go wrong in a way that can't be fixed just by reprogramming them, then there's no way to fix them. If you have a person there, then great, you can say, oh, push this button, change, replace this part, fix it, and it'll work. On the other hand, if you have people involved in the loop, then you have to worry about safety in a way that you can be perhaps slightly less worried on a robot. So for our robotic missions, if it's looking like it's broken, we might try a few different experiments to fix it. And as long as we're convinced that it's not going to completely damage the whole satellite, we'll try them. But if it's a spacecraft with a human on board, you have to be a bit more careful. On the other hand, having a person there, people can think for themselves, they can react, and the best way to deal with problems in an emergency context is to have well-trained people in the right place. So as long as your astronauts are well-trained and they know what they're doing, then it's good to have them there.
Fantastic. Team 2, I don't know if you've got any more questions you want to put in the chat box. Oh, there we go. There's one right now. When designing and building a spacecraft, what considerations do you take for living areas and living conditions for the astronauts?
This is one of those trade-off questions. Depending on how big your rocket is, you can afford to take more or less space with you. So ideally, you want to give the astronauts as much space as they need, but that costs money because space is heavy. You need the materials to make the enclosure, and that means you need a bigger rocket. So everything costs money. So it's a trade-off between mass, cost, and the needs of the astronauts. So it's usually viewed as in a kind of minimal way. What is the minimum space requirement for these people? And that will be air for breathing, water and food, for obvious reasons, and then an amount of space that allows them to move around enough to not feel trapped, I guess, and have that exercise space they need as well.
It's interesting you mentioned air there, because there was a very infamous accident during the Apollo missions, if you want to tell us about that.
Oh, wow, I can try. Yes, I mean, which Apollo was it? 13?
No, Apollo 1
Apollo
initially. So when they were making considerations for how much air they wanted to take, they thought, oh, fantastic, we can save space by just putting pure oxygen rather than just air, which is only a small percentage of oxygen. So we'll save space like that. And obviously oxygen is incredibly flammable and explosive. And so during a ground test on the ground, when they were just checking out how things work, there was an electrical spark from something, and 3 astronauts died in an accident on the ground in preparation for that. So since then, NASA haven't used pure oxygen on board to save space, because obviously it can result in accidents. So sometimes it might be, unfortunately, things going wrong that inform how we then plan for missions in the future. And you have to make that trade-off again about the safety of your astronauts compared to saving space or being able to put more things on your spacecraft.
The other thing that astronauts like is windows, which actually are a terrible idea on a spacecraft because they are weak points in your outer shell. It's things like that. If you could get away without windows, you might think that you had a better mission, but all of your astronauts might hate you for doing that. So you do have to think about the needs of the astronauts as people, as well as just mechanical and physiological needs.
And also windows can be quite useful for orientating yourself when you're on board. I know the Apollo 13 mission, they used lining up with what they could see the Earth out of the window in order to get themselves back on track. So, but I know that also micrometeorite strikes are a problem for windows.
Yeah, well, that's a whole other question. Again, the design of manned missions have to have lots of shielding around the outside to protect you from space debris. But if you're a robotic mission, you don't necessarily worry about. And again, windows are a weakness there. They use, I don't know, sextuple glazing or something. So it's as tough as glass can be, but it's still weaker than Kevlar shielding that you have on the rest of the spacecraft.
So team 1, I think this will be, we'll take one more question from each team, and I think we'll be out of time. So team 1, if you have a final question for us.
How could expandable spacecraft allow more experiments to be packed into space, and how that could have an effect on how you tackle building the experiments.
Mm-hmm. Interesting question. I think I would say when you're designing your mission, you have to justify that. You know, how are you going to use the expandable parts of your design to your benefit? I know that there is already a design for an inflatable space station, and these are certainly interesting ideas. You know, the rocket fairings are only so big, so you have to launch lots and lots of rockets if you want to build something like the International Space Station. So if you can compress something down, like James Webb Space Telescope, for example, that's a huge telescope, but it folds up into a small space. So that's really advantageous for launch, because you can get it on one rocket instead of 5. So it is an excellent idea to try and have some kind of compressible or expandable a vehicle or space station. It's definitely a good idea, but you'd have to trade off mass, power, safety, cost, and all these things, and show that it was a good idea. So it's about answering all those different questions and saying, this will be cheaper because, this will be safer because, this will be lighter because, and being convincing in those answers.
Yeah, I know that there's a very famous mission, the Shuttle Radar Topography mission, which was on the space shuttle, and that had a big, long extending boom for their radar instrument that was like very, very long. And there were arguments about whether or not this would work, and it was such a big thing to go out. And it was obviously the more things that you have, the more things that can go wrong if you've got folding and moving parts. And I think that data set from that mission remains the most downloaded science data set that there's ever been, because it mapped pretty much the whole surface of the Earth in that one mission. In about 11 days, they mapped the whole surface of the Earth. So again, they must have had a strong proposal that this was going to be useful and lots of people are going to use it.
Yeah, the reason that space agencies would be nervous about those kind of ideas is they care about heritage. If you're doing something very new, very different, how are you going to prove that it's 100% going to work? So the problem with expanding space stations, for example, is that ESA and NASA, for example, have never done that. So they don't necessarily know how it would work and aren't necessarily convinced that it will be safe and reliable. So this is why you get private companies launching inflatable space hotels. They may want to make a space hotel, but actually, if they can prove that it works and that it's safe, they can then sell that technology to NASA and ESA and other people like that as well. So that whenever you're designing a new thing for use in space, you have to go through this technology validation process and prove that your technology is going to work and be reliable.
Okay, fantastic. And then our final question from Team 2 is, do you think the upkeep of spacecraft can be made easier for astronauts to handle in terms of keeping the spacecraft safe to reduce stress?
That's definitely a good idea. And as much as possible, those kind of design considerations should be taken into account, but it's always going to be difficult. Astronauts cannot survive in outer space outside of the vehicle. So there will always be some parts that are going to be very, very difficult to repair. Whatever you can do to, as you say, to make the upkeep easier is definitely a good idea. But this is like any design process. I mean, if you look at how iPhones have evolved over the last 10 years, you see the design improving and improving and improving in terms of usability, interface, and things like that. And we need the same process to occur in space technology, but it's not normally as high up the agenda as it is for a company like Apple, where they sell their products based on this. So there's definitely space in design of astronaut carrying vehicles for a kind of interface and human interaction design goals, which I don't think have been very completely addressed so far.
Okay, thank you very much, Dr. Robert Wicks, for coming and joining us today, and thank you very much to you for your questions and for listening to us. It's been a real pleasure. And please do email over any questions you want answered, and we'll try and get back to you. And thank you very much for joining us today. We'll see you again soon. Thank you.
Thank you very much.
Bye.
Thanks, bye.